this lesson we're going to look at an investigation of quadratics. So this is going to involve some technology, so this won't be done by hand. If you have a graphics calculator, this is a good time to start playing around with it and getting familiar with how to use it for graphing functions and finding values. Otherwise, something like Desmos or GeoGebra is a really good tool and will also be able to do this. What we're going to do for this investigation is really just follow these steps. So it's giving you a step-by-step process, but as it says, you're using a graphing package to do this versus a theoretical calculation. So we're looking at graphing quadratics that are in the form of this. So A, x minus p, x minus q. And we're actually going to look at some really interesting results that come from this. So what I want you to do is just follow the process. So it says use technology to sketch. So you can use something like GeoGebra for this. Plug in this function. You can just write it exactly like this and it'll graph it for you. So sketch all of these. Something like Desmos or GeoGebra in particular lets you turn these on and off so you can switch between them. Then it says to find the intercepts for each function. So just make a note. So using your book, just make a note of this stuff as you go. What's the significance of the a? So what do you notice about the a in all of these functions? So in this case, this a would be 1, 2, minus 1, minus a half, minus 3. And we want to know, what has that done in all of your graphs? What's different about them? All the other values are the same, x minus 1, x minus 3, but we're changing the a value. So what does that do? Then it says sketch these graphs. So x minus 1, x minus 4, minus 3, minus 5, so on and so forth. Find the intercepts for a again. What is the significance of the p and the q? And so p and q, just to remind you, is up here. These are our intercepts. So the minus p minus q, what's changing between these? Now we're repeating sort of the process, using the technology sketch this. So what we're doing is we're looking at almost perfect squares. X minus 1 all squared, x minus 3 all squared, x plus 2 all squared. Finding the intercepts again, then what is the significance of p? So if we have a perfect square, what is the significance of this? What is the p doing? Then copy and complete the statement, then hit blah blah blah, the x-axis at, blah blah blah. Follow that step. Part 2, again we're using technology, we're doing a very similar thing. So part 2 is saying sketch these things, so these are all the functions with the squared rather than two separate x-intercepts. What's the significance of a again? Repeating, find the coordinates of the vertex, significance of h and k, so k is the plus something, h is the thing in the brackets, and then again finishing the statement. So once you've done all of this, or pause the video before you look at the solutions, because I'll put the solutions up in just a second, but have a go at both of these investigations, then I'll show you the solutions. You can check that with your work and we'll talk about it. So the results of this investigation are here. Ultimately what we're looking at is if we have a quadratic in the form of this, so x minus p, x minus q, where our x-intercepts are different, what we find is that, we already knew this, the x-intercepts are p and q, the axis of symmetry, so the vertex, the axis that lies on that vertex, is p plus q divided by 2. That kind of makes sense, because intuitively we said it's a symmetrical function, and if we know that we've got an intercept here and an intercept here, the symmetry has to be exactly in between, so the midpoint. And so we find a midpoint by adding the coordinates and dividing it by 2. So, therefore, the vertex has p plus q on 2. So p plus q divided by 2 gives us the vertex x coordinate. If we have this squared expression, then what we find is it touches the axis at h. 2 solutions means it crosses. 1 solution means it has to just touch. The axis of symmetry is then x equals h, because if it's touching that point has to be the vertex. And therefore we can say that the vertex is going to be h0 in this case. If we then use the same function but we add a plus k, we find that the axis of symmetry is still x equals h. The vertex is now hk. What this means is the k is just displacing the quadratic up or down by that value. So if you play around with this on GeoGebra or Desmos, write a function and then change this value. As you increase k, you should see the graph moving. As you decrease k, you should see the graph moving. So k is a displacement. It's the word we use for displacing up, down. We can also see later that you can displace left and right. And in this case, we were just using this to find a shortcut for the vertex x coordinate. To summarize this, things that I would put on a formula sheet that kind of reinforce what we're talking about. If we have this quadratic function, y equals ax squared plus bx plus c, a greater than 0 produces a smiley face, a less than 0 produces this shape here, so this concave down versus the convex graph. So they're using concave up, concave down. It's also fine to say this would be convex, this would be concave. There's different terminology. So if a is negative, we get a negative. Remember I talked about earlier the smiley face analogy? This can be really helpful because if you are negative, you are sad. If you are positive, then you are positive. The graph is positive, it's smiling. So sad graphs are negative functions, happy graphs are positive functions. The next thing is if a is between 1 and minus 1, the graph is wider than the y equals x squared that we looked at the start. If a is less than negative 1 or a is greater than 1, the graph is then narrower. So we can tell whether it's skinnier or wider than the standard y equals x squared based on where a sits. This is not as important. We don't really care too much about the width because we can kind of sketch it once we know the vertex and the intercept anyway. So that was the sort of the result. That's not the answers for each of those questions, but that's the key thing that we wanted to discover within this investigation. Next lesson, we're going to start breaking this down more and using equations to solve these quadratics, but here's some really interesting concepts that we learned in this investigation.